Hello, everyone. My name is Raghav Tulshibagwale, and I'm part of the Core Data Path group at Nutanix. Today, we would like to share our experience of the journey with RocksDB, a popular open source key value store, becoming one of the fundamental building blocks of the Nutanix offerings. Let's understand what drove us to use RocksDB in the first place. The Nutanix core solution is a hyperconverged system that unites compute, networking, and storage as a unified appliance. This converged solution leverages local components and creates distributed platform for running workloads. The Nutanix CVM is what runs the Nutanix software and serves for all the I/O operations for the hypervisor and for all the user virtual machines running on the host. This software interacts with all the hardware components on the host to provide a hyperconverged capability. Together, a group of Nutanix nodes creates a Nutanix cluster that is responsible for providing the data and control management capabilities. From the user's point of view, there is a single logical endpoint, but beneath it, there is a cluster of nodes that makes access to local and remote data seamless. The user-facing Nutanix product is extremely simple to deploy and use. This is primarily possible through abstraction and a lot of automation and integration at the software layer. We'll just talk about only a few microservices for this session. Stargate is the first service that is responsible for all the data management and I/O operations, and is the main interface between the hypervisor and Nutanix software. This service runs across all the nodes in the cluster in order to serve localized I/Os. Cassandra manages all the cluster metadata in a distributed ring-like manner using the Paxos algorithm to enforce consistency. Curator is another service that runs on every node, which is responsible for all the background tasks, including garbage collection and drives data transformations. The last and one of the most important services is Zookeeper, which performs configuration management and provides fundamental distributed system recipes like liveness, distributed locking, and many other things. But for this session, our focus is going to be mainly on Stargate, which is the main I/O engine for the distributed storage fabric. Within the controller VM, the Stargate process is responsible for handling all the I/O operations coming from the user VMs. The write characterizer determines if the writes get persisted to the extent store or to the oplog. Similarly, for reads, the read characterizer is responsible for handling reads and managing caching and read ahead. The oplog is built as a staging area to handle burst of random writes, coalesce them, and then sequentially drain it to extent store. The extent store is the persistent bulk storage of the distributed storage fabric and spans across all the tiers. It is responsible for disk management, data storage, and various data transformations. The unified cache is a read cache used for both data as well as metadata. Now let's quickly jump into an anatomy of a write. Here, we show how an extent store persists a write by using a 4-controller VM example. The first node acts as the coordinator of the write operation. It initiates a global transaction, which is recorded by Cassandra, and that translates to 3 internal network hops and 3 disk IOs to support a complete round of Paxos protocol. At this juncture, the extent store on CVM1 initiates a local transaction and triggers a parallel local transaction on the extent store, which on replica CVM2. As part of the local transaction, the expected change to the data is logged locally, which translates to disk IOs. Once the local transaction has started, the data is returned to the persistent medium, triggering its respective disk IOs. The local transaction is marked complete after the data is written. The global write marks the overall operation as complete, which again translates to writes to Cassandra. It is pretty evident from this that this is a really long I/O path where the amplification can be up to 12 times for a single outstanding user I/O. Nutanix engineering has been working on three major goals for its distributed storage fabric. Improve the sustained random write performance. On many performance escalations, we saw that the extend store was not able to drive the desired sustained random write performance because of high write amplification and involvement of the metadata store in the I/O path. Given the falling prices of the spindles and proportional increase in their capacities, supporting deep storage nodes for use cases like object storage, long-term storage services, and backups became an important priority for us. The background data management system curator that uses metadata to make its decisions based on reading and scanning the metadata became increasingly costly because the cluster sizes grew. Overall, the cost of global metadata management to support various use cases was increasing. As we outlined these goals or requirements and the long I/O path that we saw in the previous slide, it became increasingly clear to us that we needed a fundamental change to the architecture of the extend store. Bring the metadata closer to the data became the foundational principle of redesigning the extend store. In other words, make the extend store autonomous, so it can make decisions about local data using local physical layout metadata instead of consulting the global distributed metadata store. This change would enable individual nodes to host extend store data modifications and provide local background data management. But to achieve this, we needed a database or a key value store that could be deployed locally on a host where we could move all the physical data layout metadata from the metadata store. Given the increasing sizes of the disks, each disk would become an autonomous storage system capable of managing its own data as well as metadata. But what were we looking for from the key value store? This local metadata storage system required a completely new view. We had the following goals when we started researching for a potential database or a key value store. It should be able to reside in the same address space as the extend store service to achieve co-located data and metadata. It should be highly write optimized backend with acceptable read performance. It should be able to support lightweight ACID properties, which are typically provided by databases. And finally, it should be able to provide the same external APIs similar to Cassandra so that we can reuse the interfaces to access the metadata. RocksDB. RocksDB was the answer that we were looking for. Let's see why. RocksDB, being an embeddable C++ library, allowed us to link it with extend store and set us for the key value store inside the same address space, which allowed co-located data and metadata. Given our strong familiarity with log structure merge tree architectures due to Cassandra, the RocksDB key value store became an obvious choice. LSM storage engines are highly write optimized and provide acceptable read and scan performance, which supported our goal of improving sustained random write performance. RocksDB also provides very similar APIs to Cassandra, where the data is stored in terms of keys and values. And this allowed us to use the existing metadata store interfaces. Support for write-ahead log-based persistence, data checksums were crucial for us. RocksDB support for ACID properties through write batch support and snapshot isolation with semantics similar to multi-version concurrency control made it really attractive. One of the most essential and vital features of RocksDB is a pluggable persistence layer, which is called as the ENV, which allows RocksDB to be deployed on any file system like backend. And then finally, one of the most important factors, RocksDB's active open source community, which is supported by organizations like Uber, Airbnb, and Netflix, further boosted our confidence in RocksDB. To bring the metadata closer to the data, we redesigned the metadata store and brought the metadata from the original distributed metadata store to inside the extend store. We used a multi-embedded databases model where each database is a RocksDB instance. The extend store is one of the components of the IO store and manages all the data disks hosted by that machine or node. In this mode, each disk hosts its local metadata in its RocksDB instance backed by the same disk. We call this newly redesigned extend store as the autonomous extend store, as it manages its data as well as metadata. And each RocksDB instance is called as the autonomous extend store database. Now let's take a quick look at the new write IO path. We can clearly see that the number of over-the-network IOs and metadata writes have significantly reduced. The metadata updates are now stored in a local key value store called as AESDB, and they are written asynchronously to it. This clearly provided the boost in performance that we are looking for. It should be pretty evident from these numbers that the sustained random write performance saw a significant improvement. We could typically see up to 8 to 10x improvement on various deployments. This would not have been possible without the re-architecture effort and use of RocksDB. Said that, each coin has two sides. We got the best out of RocksDB, but we also had a lot of learnings along the way. In the next set of sections, we'll go over some of these learnings and improvements we did to RocksDB. Thank you.
Hello everyone, my name is Pulkit Kapoor and I work in the core data path group at Nutanix. In this section, I'll be talking about the RocksDB synchronous and asynchronous read and write APIs along with their performance numbers. Let's go over the basics first. Memtable is an in-memory buffer that hosts the incoming writes. If write-ahead log is enabled, each write is first persisted in the log storage before being written to the memtable. As the size of memtable reaches a threshold, it is converted into an immutable memtable, further flushing it to storage, generating a AESDB file. This AESDB file is immutable in its lifetime. Also, we have a background thread performing compaction of AESDBs to larger AESDBs by getting rid of the garbage. Now let's go over a typical read path. We start by looking for the desired key in the mutable memtable, immutable memtables, and the AESDB files from the newest to the oldest, which might result in multiple disk IOs. Limitation of such read APIs, which includes get, multi-get, scan APIs, is its synchronous nature. Client threads issuing reads are blocked within RocksDB while reading from disk or acquiring DB logs. In this slide, we compare the synchronous versus asynchronous version of read API. On the left, we show the sync version of the API. Client thread sends a read request to RocksDB that ends up performing the blocking disk read. On the contrary, in the async version, client thread with the read request offloads a request to a separate RocksDB read thread. While the read thread is performing the blocking read, the client thread is free to do some other work. Once read is complete, client thread is notified of the read result. Our requirements from the API was to allow asynchronous programming model to be used for better thread utilization by avoiding to block physical threads for disk IOs, network IOs, or while acquiring logs. This model allows us to achieve the same or maybe better performance without shedding too many threads to the process. To achieve this, we utilize Nutanix fibers, which are coroutine style, cooperatively scheduled application threads. Each fiber has its own CPU state and its stack, but needs to be scheduled on host thread, such as a POSIX thread. When a fiber needs to block waiting for an event, it returns control back to the host thread, which is free to pick up some other work. With fibers and Linux asynchronous IO, we were able to design non-blocking reads using vanilla RocksDB code. Now let's take a look at the RocksDB read path with Nutanix fibers. We have a read fiber pool, which manages a pool of fibers and uses a bunch of host threads as its provider. All the read operations are added to the pool along with their done callbacks while the client thread runs. Fiber executing on a host thread picks up the read operation and issues it to RocksDB. It ultimately submits the IO to the asynchronous IO pool. At this point, the fiber blocks itself, waiting for the IO to complete in background, while the host thread is free to pick up new work. Once the IO is complete, Host thread resumes a fiber from where it left off. It invokes the done callback to let the client know of the read operation completion. Through this, a single thread is able to provide multiple outstanding IOs. Here we compare asynchronous and synchronous read path throughput with effective number of outstanding read operations. For synchronous read path, which is the default RocksDB read path, number of outstanding are maintained with equivalent number of threads with no fibers enabled. For asynchronous read path, a single thread can maintain any number of outstanding. In this experiment, we have measured throughput for asynchronous reads with 1 and 2 threads as the provider to the read fiber pool with different number of outstanding operations. We observed that the asynchronous read performance with single or 2 threads and fibers enabled is slightly lower in comparison to synchronous read performance with multiple threads equal to the number of outstanding ops. Hence, with far less number of threads in the system, async reads are able to achieve considerable read performance. Similar to last experiment, in this slide, we compare asynchronous and synchronous read path latency with effective number of outstanding read operations. We observe that the asynchronous read latency with single or 2 threads and fibers enabled is slightly higher in comparison to synchronous read latency. Now let's talk about RocksDB write path. Say we have 3 threads that arrive within RocksDB with a write operation. The first thread is chosen as the leader while all the other threads become followers. Followers spin for a while, followed by blocking itself, while the leader does a bunch of work for the group. It pre-processes the writes, checks if it needs to switch to a new mem table, switch to a new wall, or maybe schedule a flush. Creates a write patch group. Here it combines itself, F1 and F2 into one write patch group. If wall writes are enabled, it issues a wall write followed by a sync, post which it signals the followers in the current write patch group to parallelly write to the mem table. Say F3 enters a RocksDB with its write. It is simply blocked till the previous write patch group completes. Leader F1 and F2 complete parallel mem table writes. Wait for the last thread in the write patch group to finish mem table write by spinning and followed by blocking. Say F1 is the last one to finish the mem table write. It gathers all the results from the other threads in the patch group, updates the sequence number, and signals the other threads in the write patch group to complete their write. It as well signals F3 to become the leader for the next write patch group. Disadvantage with the current approach is that follower client thread spin or block itself in the worst case in multiple scenarios. This spinning simply leads to CPU wastage. Our approach to solve this problem was by adding a single threaded thread pool inside RocksDB. Client thread adds work along with the write and callback to the write thread pool and returns. Thread pool thread within RocksDB combines a bunch of writes into a write patch group, performs leader duties, sequential writes to mem tables, as their simple in-memory updates, sequence number updates, and invokes the write and callbacks, marking the completion of the write. Now the writer thread is free to pick up the next write patch group. Here we compare asynchronous and synchronous write path throughput with effective outstanding write operations. For synchronous write path, a fixed number of threads are needed to generate the same number of outstanding operations. For asynchronous write path, a single thread is enough to maintain any number of outstanding operations. This is because the client threads are not blocked within RocksDB while performing the write. The write is offloaded to an internal RocksDB thread along with the done callback. All the writes are happening in a VM environment on a vDisk for this experiment. We observe with increasing number of outstanding operations, asynchronous write path is able to match or even exceed the synchronous write performance. In this slide, we compare asynchronous and synchronous write with CPU utilization. Since there are far fewer threads in the system needed to generate the same workload in case of async write path, this reduces the CPU utilization greatly. Thank you, everyone. Now I'll be handing off to Yashasvi, who will be talking about RocksDB scale problem. learnings, and solutions.
Hi, everyone. I'm Yashasvi, and I work in the core data path team at Nutanix. In this section, as Pulkit mentioned, I'll be taking you through some of the learnings that we went through with RocksDB at scale. So as the scale of our deployments with RocksDB grew, gaps started showing in our system. We started seeing performance and stability concerns as database sizes went into hundreds of gigabytes. Specifically, we were able to narrow down on 3 critical problems: higher than expected memory usage, sustained write performance issues due to write stalls, and scan performance issues. I'll walk through each of these problems and how we were able to overcome them. Let's start with the memory footprint problems by looking at how each RocksDB SSTable file consumes memory. Each SSTable comprises of 4K sized data blocks which store the key value pairs. We then have 2 level indexes for efficient lookups. To minimize unnecessary lookups, we also have a Bloom filter per SSTable file. Index blocks go into an LRU cache called the block cache, and Bloom filters are pinned in heap outside the cache and can grow as a function of the database size. But these were not adding up to the peak 6 GB footprint that we were seeing. We found that the problem was actually due to bloat during Bloom filter construction. While creating a new Bloom filter, RocksDB needed to buffer all the hashes in memory before populating the final bitmap, which was 4 times larger than the Bloom filter itself. Let's now understand the scan issue with this example of a database, which has a few duplicates and deletes. Since SSTables can have overlapping ranges in keys, we need to iterate through all the files and merge the results using a heap to finally return the right results back to the client. In this example, reads from SSTable 2 and 3 will end up being wasted for keys K1, K2, and K3. And to finally return 3 keys back to the client, we ended up reading all 9 keys from the database. So when the database size goes into billions of key value pairs, garbage too can grow into the order of millions of keys, at which point we saw RocksDB scans take minutes to complete, which led to timeouts and retry storms. These retry storms caused pressure on resources and led to the overall system becoming unavailable. We introduced circuit breakers on deadlines to mitigate this issue. However, this did not solve the problem of scan unavailability in the setup. We needed compactions to get rid of this garbage and bring scan performance back to where we like it. However, RocksDB not having a garbage-based heuristic, as well as a lack of a feedback mechanism to have scan performance as a heuristic, meant that the duration of unavailability ended up as unpredictable. To address this gap, we brought in a new component above RocksDB called the Background Task Manager. Its chief responsibility was to track garbage and take corrective actions as needed to keep scan unavailability as low as possible. It proactively polls RocksDB to calculate the amount of garbage and decides if it needs to trigger corrective action. In case there is a delay or gap not covered by the heuristics, we then have a feedback mechanism built in where scan slowness due to garbage will always trigger corrective action. Corrective action may be a combination of flush and compaction if the deletes are in the mem table, or just compaction if the deletes are mostly in the on-disk SSTables. Let's now come to the write stalls problem. In LSM systems, good read and scan performance needs the number of SSTables to be at a small manageable number, for which we rely on compaction. If compaction can't keep up, we end up having to throttle writes. But getting into the state goes against our core design principle of supporting sustained random writes. But first, let's see how this happens more frequently at scale. With this example of a database, which has 101 GB of data spread over 4 SSTable files. If a compaction begins for this database, this may be due to garbage or any other heuristic, this would take tens of minutes to complete. However, fresh writes will continue to come in, which will cause new files to be written, and this will take us over the limit very easily. While parallel compactions would have helped here, unfortunately, due to the memory bloat we talked about earlier, supporting parallel compactions was not possible at this stage. So now that we've talked at length about the issues that we've hit at scale, the requirements from compaction became much clearer to us. We needed to find a way to limit memory overhead, which could be achieved by limiting the maximum size of each assistable file. This would give us a way to enable parallel compactions. We also needed a way to reduce I/O amplification further to minimize the bandwidth effect of parallel compactions and garbage-based compactions on the disk. Our existing strategy of universal compaction with a single level was not serving our requirements well. RocksDB offers leveled compaction as another possible strategy, but it was ruled out due to its much higher write amplification of over 3 times. To get the best of both worlds, we chose to use universal compaction with multiple levels. So as you can see with the diagram, the layout of the database now changes. All new SS tables will now go to the logical level L0, due to which we will still have files with overlapping ranges in this logical level. However, we will have additional logical levels which has colder data, and that will have files with non-overlapping key ranges, and these files can have a fixed size. This strategy allows us to clear more data out of L0 into lower levels and can help us keep L0 much smaller. This also allows us to cap the size of all SS tables in L1 and above, which allows us to reduce our memory bloat significantly. This will help us enable parallel compactions and in turn minimize the number of write stalls that we hit. However, we still have the problem of higher write amplification and its effect on SSD life. Since we are triggering compactions more frequently to keep garbage in control, this becomes very important. An optimization that is possible with this layout is that compaction only needs to rewrite files which have overlapping ranges. So in the diagram, you can clearly see how the last 3 files in L1 do not overlap with any other file and thus need not be touched. This again helps bring down I/O amplification. We measured both memory bloat and I/O amplification by writing over 300 GB of data into a single RocksDB over 24 hours. And we were able to cut down memory bloat from 3 GB to under 200 MB. And our write amplification also saw a marginal improvement. We expect the improvements on write amplification to go up further as the system ages over weeks and months. These changes are what enabled us to use RocksDB as a technology at any scale across all the new use cases at Nutanix. Thank you. I'll now be handing off to Sandeep, who will be talking about ChakrDB, our next generation distributed key value store. Thank you.
Hi, everyone. I'm Sandeep, and I work in the core data path team at Nutanix. As we were tackling issues with single instance RocksDB and making improvements there, we encountered services which required high performance, linearly scalable, cloud native, and distributed key value stores. So we took RocksDB to the next level and made ChakrDB a next generation distributed key value store. I would like to start with the motivation for ChakrDB. Nutanix Distributed Storage Fabric was built with web scale, scale-out design, which can easily scale to petabytes of storage with high availability, resilience, and fault tolerance. With the advent of the world of containers, the compute infrastructure management was moving towards Kubernetes to bring high availability and fault tolerance into the compute layer. Such a platform has become a building block for Nutanix next generation offerings like files, objects, etc. These new age highly distributed microservice architecture based cloud native services required a scalable distributed database to store and manage their metadata. Let's discuss the requirements of such databases suitable for cloud native services. Many of these cloud native services need their metadata layer to offer low latency and high throughput, even at larger scale and higher working set sizes. At the same time, it has to be highly efficient with resources, as traditional NoSQL DBs are not known to be good at resource efficiency. Database has to be distributed and should scale linearly. Being a critical storage system, database has to be highly consistent and satisfy traditional ACID guarantees. At the same time, the system needs to be resistant to any form of data loss. The distributed database has to work on any cloud or platform. It has to be containerized and optimized for the Kubernetes world to be truly cloud native. Many of the new age cloud native applications today have use cases to tier their cold data to remote cloud such as S3 or store data remotely in cloud such as EBS, Azure Storage, etc. To support all such use cases, it's important for the DB to support remote storage. Being an infrastructure software, all the DB workflows have to be single-click driven. This has been another core design principle for most of Nutanix software. Now, with the above requirements in mind, we wanted to build a database for cloud-native services. So we came up with ChakrDB. ChakrDB is a distributed NoSQL key-value store. It incorporates virtual nodes-based sharding design, which we believe is a very powerful concept which enables linear scalability with high throughput and better tail latencies. Each vnode is a wrapper on top of RocksDB and has an entire key-value store stacked by itself, making it independent. This design makes the cluster truly elastic as it can be expanded or shrunk seamlessly by simply moving around the vnodes. ChakrDB is designed as a lightweight shim layer on top of set of RocksDB instances, inducing no overhead in the IO path. ChakrDB is designed on top of RocksDB, which is an LSM-based key-value store. LSM data structure is optimized for SSDs and also opens window for several new storage technologies and new architectures, making it future-proof. Also, virtual node architecture of ChakrDB is quite flexible, wherein each vnode encapsulates RocksDB today as storage engine. However, it can be replaced with some other engine tomorrow. Design enables us to do that. So this is how a ChakrDB instance looks like. A ChakrDB instance is a single process or a pod or can be a container that embeds multiple vnodes in it. Each vnode owns a shard in the cluster. It supports both ext4 file system-based volumes and also a Nutanix internal plain block-based file system exposed by the Nutanix distributed storage fabric. It has several internal modules. API interface exposes key value-based APIs today and can expose more feature-rich APIs going forward. Schema Manager handles schema and orchestrates schema manipulation workflows in the cluster. Background Task Manager, as discussed in the previous section, is responsible for tracking the performance of vnodes and taking corrective actions when required. vNode Manager manages and orchestrates all lifecycle operations of vnodes, such as bringing up a vnode, bringing down a vnode, etc. This is a high-level architecture of ChakrDB cluster. ChakrDB instances can be deployed as pods on Kubernetes platform. This platform can be hosted on Nutanix distributed storage fabric or any cloud storage per se. There are three major components in the ChakrDB cluster. ChakrDB instance hosts the vnodes and their respective storages. It is a core piece which manages the entire data path. Storage for vnodes are backed by distributed storage fabric, be it from Nutanix or EBS or Azure Storage. Chakra Cluster Manager manages all the control plane traffic in the ChakrDB cluster. This module makes majority of the decisions in the cluster, such as number of ChakrDB instances to start the cluster with, number of vnodes hosted inside a ChakrDB instance, mapping of shards to vnodes, and so on. It creates all this configuration and stores it in the configuration store. And the last is configuration store, which persists all the ChakrDB configuration. Client services can use ChakrDB client library to talk to ChakrDB instances. This client library fetches the shard mapping from configuration store and uses that information to send the request to appropriate ChakrDB instances to avoid extra network hops. ChakrDB works in both embedded and remote modes. In embedded, client services can embed the ChakrDB instance into their process, which would avoid RPC overhead. we have tried the embedded approach with Nutanix objects. ChakrDB can be scaled linearly both inside and outside, which means vnodes can be scaled within a ChakrDB instance, and at the same time, ChakrDB instances can scale themselves linearly, expanding the cluster. While ChakrDB is running in the production, deployed as part of Nutanix objects, here are some of the numbers from our internal clusters. Largest cluster deployed by our QA had around 1024 ChakrDB instances with 4 vnodes in each ChakrDB instance. This amounts to around 4,000 vnodes in total in the ChakrDB cluster. One of our internal cluster went up to pushing around 25 terabytes of data with around 75 billion keys in 128 node ChakrDB cluster. This translates to around 200 gigabytes with 600 million keys per ChakrDB instance and 50 gigabytes with 150 million keys per vnode. A ChakrDB instance with 11 gigs of memory was handling around 8 billion keys and around 1.6 terabytes of data. This instance had 8 vnodes in it, where each vnode was holding around 230 gigabytes of data with 1 billion keys. This shows the resource efficiency of ChakrDB. Most of these ChakrDB clusters were deployed on a 4-node Nutanix distributed storage fabric cluster. This shows how ChakrDB utilizes full potential of distributed storage fabric. This slide talks about the true power of linear scaling. This shows the throughput seen with scaling ChakrDB instances linearly. However, we'll continue to work on increasing these numbers. Currently, we are working on scaling out instances dynamically on a live cluster. This will enable us to scale the cluster seamlessly with zero or very less impact on the user I/O. We are also working on providing secondary indexing support for ChakrDB. This feature helps clients increase the performance of their queries that do not rely on the primary keys of the table. There is work in progress to replace Cassandra with ChakrDB in our core Nutanix distributed storage fabric to overcome the issues and bottlenecks seen with Cassandra. One of our internal products for its solution to cloud-backed disaster recovery is working to use ChakrDB for its metadata local caching requirements. As part of it, we are working on running ChakrDB on Azure Kubernetes Services platform. There's also work in progress to integrate ChakrDB as storage engine for one of our control plane databases, which stores time series data. Some of the work which we are planning to take up in the near future includes distributed transaction, which is a powerful feature used in traditional databases in single instances. However, supporting transactions across shards and instances in distributed fashion is not a small feat. We'll make our efforts to support this for ChakrDB. Postgres supports pluggable storage engine. We would like to replace its default storage engine with ChakrDB, which will give way for distributed Postgres with scalable storage engine. Another task which we want to pick up is to open source our work with ChakrDB. This is back in our mind since we started working on this project. However, we started off pushing back some of our changes and enhancements into open source RocksDB. I would like to end the talk with discussing our vision for ChakrDB. We have discussed about the new age cloud native services and their requirements. While majority of their requirements are satisfied by a distributed key value store, they do have other subsystems which might require a time series database to store their stats, or a rich query layer to support analytical data, or relational database which is ACID compliant, and so on. It made us clear that we needed a single stop shop for all system that could serve these data models along with adhering to the fundamental principles of cloud-ready services. This system consists of two parts. The top part covers various data models to support, while the bottom half, which manages a persistent state, is common for all and should be able to run on any cloud. ChakrDB can fill the bottom half for various data models as highly distributed and scalable storage engine. In most of the distributed databases, their performance and features are mostly determined by the efficiency of the underlying storage engines and the flexibility it provides to support the features. Now that we have built ChakrDB as scalable, distributed, high-performance storage engine with support for key value APIs today, we believe it can be extended to work as storage engine for any other data model such as document model like Mongo, row column based like Cassandra, relational like Postgres, and more, giving way for a truly multi-model database. We're also planning to publish a series of blogs on ChakrDB. You can refer to them for more details. Thank you all. We are open for Q&A. For any queries or more details, you can contact us at rocksdb@nutanix.com.